Assalamualaikum warahmatullahi wabarakatuh. Today topic is buoyancy. Okay, this is list of reference that you might refer for this topic. This topic have 6 subtopics include principle of buoyancy, the equilibrium of floating bodies, the stability of submerged and also floating body, and lastly about metacentral and metacentric height. Okay, the learning outcome is you must be able to formulate and also apply the buoyancy principles of fully submerged or floating bodies to solve problems related to it. Okay, let's recall your knowledge on phase. Okay, so we can see that there is a different phase expressions of the buoy. So the first buoy, when they carry the rock inside the water, the fish is very happy because they feel lighter. So this is lighter, light, ringan. And then this is very heavy. When the object is not immersed in water or half as partially submerged, the buoy feel heavy, and that's why the expressions look so tired. Okay, and then we have to investigate the relationship between the weight and the water displaced and also the buoyant force. Then we are using Eureka can. Okay, so you can see the plasticine before immersed in water. So the weight is very high, and then when the plasticine is immersed in the water, the weight decreases. And then the Eureka can will displace some water into a beaker. So this is the amount of displaced water in the beaker. And the conclusions for this experiment is the weight of water displaced is actually equal to the buoyant force. Okay, so here weight of water displaced is equals to buoyant force. W equals to FB. Okay, how we calculate weight? Weight is rho GV. So the V here is the V object, O, VO. And then for FB also the same formula we are using. Density times gravity times V, but the V here is the VD because this is the volume displaced. Okay, only the volume that inside the water for buoyant force FB. Okay, the buoyant force is actually follow Archimedes principle where for a body completely or partially submerged in a liquid, the upward buoyant force is equal to the weight of the liquid displaced. Okay, this one is already mentioned in the previous slide, where Fb is the weight displaced, or we can calculate the buoyant force as rho g Vd. Okay, where is the Vd? Vd is the volume displaced. For example, you have a rectangular boat, and the boat is partially submerged. So only the volume inside the water is calculated as Vd. So this is the Vd. Okay, then let's discuss on the different types of buoyant force. So for the object A, we can see that how the object is rising. So the object is rising when the buoyant force is higher than the weight. Okay, then for picture B, we can see how the object is sinking at the bottom. Okay, how the object is sinking? Because the weight is higher than the buoyant force. That's why the object is sinking at the bottom. And for C and D is where the weight and buoyant force is approximately equal. So it can be partially submerged or fully submerged. For C it is half or partially submerged, and for D it is fully submerged. So the condition is the same, where the weight is equal approximately equal to the buoyant force. Okay, then 2.2.1 is introductions. Okay, what is definition of buoyancy? Buoyancy is the vertical force exerted by the fluid on an immersed body. Okay, so buoyancy also can be known as weight of fluid displaced by the body, and we use this formula to calculate buoyant force. Okay, Fb is buoyant force, rho is density, and Vd is displaced of volume. And then we should know what is the center of buoyancy. Center of buoyancy is the point which buoyancy is acting, and the centroid of displaced volume. Okay, so we have this object. So the center of the object is the center of buoyancy, where the buoyant is acting. So from the center, we have buoyant force. And also from the center, we have the weight. Okay, then this is the picture for principle of buoyancy. So we can see here we have different fluid density and also different volume. So you have also two buoyant force for object below and for object above. Okay, so we calculated the arc thrust, which is buoyancy. We need to use density of 1, gravity, and the volume of 1, acting on the center of buoyancy. Okay, so center of the object is arc thrust 1, and then we have arc thrust for lower part of the body. We use density of the below fluid, and then for G is still the same, 9.81, and use the volume at 2. Okay, then only we can total up the arc thrust. Okay, add the arc thrust for below part and arc thrust for upper part. Okay, this is how the procedure for solving buoyancy problems. So I already mentioned, first you need to draw full body diagram. Okay, so you draw like this, full body diagram at the center of buoyancy and the weight and also the buoyant force, Fb. This is for the first step. And then you must write the assumption, the vertical equilibrium is sum of vertical force is 0. Means Fb is equals to W. Okay, and then we can solve, we can find the buoyant force using the formula rho GVD, or we can determine the weight of object using rho GV object. Okay, full volume of the object. Vd is only object that immersed in water. And then you can calculate the depth of immersion, how much the object immersed, using the formula Vd divided by area. So you can find the x. And then let's go through the examples. We have a stone that weighed 665 Newton in the air. So means that the real weight in the air is 665 Newton. When the stone is completely submerged in water, the weight becomes lighter to 420 Newton. So calculate the volume of the stone. The unit weight of the stone is 9803 Newton per meter cube. Okay, so we have V actuals and V apparent. V apparent is inside the water. So we can minus V actual minus V apparent. So the difference is 245 Newton. Okay, then we do sum of V is 0. So Fb equals to W. This is Fb equals to W. Then you bring W to the right side. So Fb minus W is 0. and then you substitute the FB is 245 and use the formula for weight, rho GV object. Okay, then we can calculate how much is the volume of the object in the air. So it is 0.025 meter cube. Okay, let's go through another examples. So we have 60 millimeter cube, means a cube is the measurements is same for length, width and also height. And then the cube is immersed in water at depth of 40 millimeter from this picture. And then determine the magnitude and directions of the force required to hold the cube when we place the cube in the glycerin. And then the specific gravity of glycerin is given. So how we calculate Sg to density? How we convert specific gravity to density? We times 1000. Okay, so what we need to calculate is Fe. After we put the cube in the glycerin, we need to determine how much force that can hold the cube from sink at the bottom. Okay, so first thing first, we need to calculate the volume. The volume for immersed object, the volume that immersed, so this one. So we are not using the height of 0.06 because the immersed only 40 mm, convert to meter. And then we take functions Fv equal to 0, Fb is equal to W, and then W is rho G Vd. Okay, then we use the Vd from here. We get the force buoyancy is 1.413 Newton, and then we can know the V object, keseluruhan weight of the object using the height of 0.06, and then we can calculate for we can take summation first, F equals to 0, then we can write FB minus the FE. Okay, this is FE, and then minus W, the weight. Okay, why we minus? Because you can see the arrow. Okay, so this is positive. Okay, this is different direction, so negative. This is different direction, so negative. Okay, then we can substitute the density. Density used is density of glycerin. And then the Vd is the whole object. Okay, because whole is immersed in water, not partially immersed. And then the W is already calculated from upper here. Okay, so then we can know the force that can hold the glycerin from sink to the above, to the below, sink to the below. Okay, then let's try another question with different different density of fluid. So below we have mercury and also water. This is density 1000 for water, and for mercury is 13,600. And we need to find the density of metallic body which float at the interface of mercury with given specific gravity, and the volume is 40% submerged in mercury and 60% submerged in water. So volume for water is 40% and for mercury is 60%. Okay, first we need to calculate the weight, the total weight. So we write down weight is equals to rho GV. And then for buoyant force, we are using the C formula, but the V is the VD. So we calculate for water first. So when water, we use density of water, and we don't know the V. But we know that submerged in water is about 60%, 60 over 100, so it becomes 0.6 V. Okay, and then we calculate for mercury. We use the density for mercury, and it is 40% of the volume. So 40 divided by 100 is 0.4 V. And then how we calculate the weight? Weight is buoyant for water and buoyant for mercury. We adding. Okay, why we add? Because it is different density. So we cannot calculate together. We need to calculate the buoyant force separately. Okay, so this is buoyant force for 1. This is FB2 below, and we have another FB1 just now. Okay, and then we can get the density. Because weight is equal to rho GV, and we can substitute the V, and we get the density of 60,040 kg per meter cube. Okay, so this one I need you to try yourself first, and we discuss later in the tutorial class. Okay, thank you.